Good morning, dear students. I completed first chapter, electric charges and fields. Now we move on to the second chapter, that is electrostatic potential and capacitance. This chapter also carries 8 marks. So look at the heading, electrostatic potential and capacitance. In the first chapter we learned electric charges, electric field, then now electric potential. So electric charge, electric field, electric potential are related phenomena. How they are related, you are going to understand very clearly during the explanation. Now I am going to explain some fundamental concepts which are related to the second chapter. Now I am going to consider a positive point charge, say plus Q, placed at a point O. In the first chapter we learned that the charge produces electric field, the space around the charge. So even in this case also, this charge produces electric field, the space around the charge. In the region of electric field, I am going to write one electric lines of force or electric field line, electric lines of force or electric field line. So in this electric field line, again I am going to consider 2 points, say A and B. This line is nothing but electric field line or electric lines of force within the electric field, which is produced by positive point charge. Now I am going to place a charge at point Q, one more positive charge I am going to place at the point B. Now my question is, can the charge Q move from point A to B by itself? The answer is no. Why? Why? Because look at this, this is a positive point charge. Here also we consider positive charge only. So in between there is a electrostatic force of repulsion. There is a electrostatic force of repulsion like this. Fe, that is electrostatic force of repulsion between these two charges, which means this electrostatic force push the charge away from this charge. So this charge itself, it cannot move from point B to point A. Then what we are supposed to do? We need to apply some external force on the charge Q to displace. So what we are applying? F external. So we are using external force to displace a charge from A to B. So force into displacement is nothing but what? Work done. Which means work is needed to move the charge from B to A against electrostatic force. And one more thing we can notice, as the external force increases, electrostatic force also goes on increasing. To bring the charge Q from B to A, we are doing the work done. But work done in bringing the charge from B to A varies from point to point. For example, to bring this charge from B to a certain point, the work done be W1. To bring a charge from point B to some another point, it may be W2, which means the work done in bringing the charge from B to A varies from point to point. Why? Because the electrostatic force also keep on increasing. And one more thing, we can notice that the acceleration in the charge is 0. Why? Because so electrostatic force is 10 Newton, then external force what we are applying is also equal to 10 Newton. So we are doing the work done to bring a charge from B to A without producing any acceleration in the charge, which means we are moving with constant velocity from point A to B. Okay, so two things we understood, that is work done in bringing the charge from B to A varies from point to point, the first one. The second thing, while doing the work done in order to bring a charge from B to A, acceleration produced in the charge is 0 because we are moving with constant velocity. Now let us calculate the work done. The work done in moving or bringing, in moving a charge Q, because we are moving this charge. Work done in moving a charge Q from where to where? From B to A. From B to A we are moving against electrostatic force. Against electrostatic force is given by, so it can be calculated by using integration. So work done in order to bring a charge from A to where we are moving or bringing, B to A. So B to A. So work done equation, force into displacement, I will write in terms of dot product. F dot, you just imagine the distance between these 2 points is taken as dx. So F vector dot displacement, that is dx vector, since force work done is equal to force into displacement. So why we are using the integration means to calculate total work done in order to move a charge from B to A, since it is varies from point to point. So this gives total work done in order to move the charge from B to A against electrostatic force. And one more thing you can notice here, look at this, the work done what we are doing in order to move a charge from B to A, that is opposite to the direction of electrostatic force. In the opposite direction we are moving, which means the equation become minus, from where to where we are moving, B to A, force dot product into displacement. So here we can write the work done from where to where we are moving, B to A, like this also you can write, we are moving B to A. So we got that the work done is needed to bring charge from B to A or any point in an electric field, because there will be a electrostatic force. So against this, in order to move the charge, we require work done. The next thing, this is the first one, the first fundamental one. Second one, okay, you just imagine we brought the charge from point B to the point A. Then the work done what we are doing, that is stored as potential energy at the point A, because we are bringing the charge from B to A. You just imagine we brought to the point A. So here the work done is stored in the form of potential energy. Potential energy. Suppose if you remove this external force, this charge won't be there at a point A itself. Once you remove the external force, what will happen? This charge again go back to the initial position, that is it will go to the B. While going, it acquires kinetic energy. While going, it acquires kinetic energy. Just imagine again it moved to the point B, which means total energy of the charge remains conserved. Third point. Just now I told you that the work done what we are doing to bring a charge from B to A varies from point to point, which means potential energy also varies from point to point. There will be a potential energy difference between any 2 points. Suppose for example, again I am going to consider these 2 points, point A and point B. When the charge is at B, the potential energy B, UB. We are doing the work done. You just imagine we brought this charge to the point A. Then potential energy at a point AB, UA. So potential energy difference between the 2 points A and B is given by potential energy difference. So we can write delta U is equal to UA minus UB. So this is the potential energy difference. When the charge Q at a point B, then the potential energy is UB. When you brought the charge from B to A, the potential energy be UA. So there is a potential energy difference between these 2 points. So that is given by delta U is equal to UA minus UB. Here you are supposed to write UA minus UB only. Why? Because potential energy is higher at a point A and compared to the point B. The first point, second point and the third point. Now I will move to the fourth point. The fourth point, electric potential. It's very important. Look at the board. I consider one diagram, a simple diagram. I consider a positive point charge placed at a point O. It produces an electric field. The space around it produces electric field. In the region of electric field, again I consider electric field line. Look at this. On the electric field line, I marked one point, say A, and I just imagine a point of infinity. The point of infinity means where the electric field as well as electric potential is 0. So I consider. At the point of infinity, I imagine a unit positive charge, also called as test charge. What does unit positive charge? What do you mean by unit positive charge? Is nothing but whose magnitude is 1 coulomb. Look at this within a bracket. Unit positive charge is nothing but whose magnitude is 1 coulomb. So look at this diagram. Positive point charge placed at a point O. Within the region of electric field, I consider electric field line. So in the electric field lines, there is a point, namely A, and at the point of infinity, where the electric field, electric potential is 0, I imagine unit positive charge or test charge. Now, what we are doing to understand electric potential, we are doing work done to bring unit positive charge or test charge from infinity to the point A. Against electrostatic force, we need to do work done. So what we are doing the work done in order to bring unit positive charge from infinity to point A against electrostatic force without producing any acceleration in the charge is known as electric potential at a point A. Look at the statement. Electric potential at a point means A only. In an electric field, see, in an electric field, I marked a point A. So in this point only we are finding electric potential. Electric potential at a point, that is A, in an electric field is the work done in bringing a unit positive charge or test charge from where to where we are bringing, from infinity to that point. To that point means the point what we marked. Against electrostatic force, I told you no, against electrostatic force without producing any acceleration in the charge. So what we are doing, the work done in order to bring a unit positive charge from infinity to that point, that gives electric potential at that point. So mathematically we can write the equation for electrical potential as like this. V is equal to work done from where to where we are bringing, infinity to the point A, divided by Q naught, that is unit positive charge. So like this also we can write V is equal to W by Q naught. The fifth point, potential difference. Again we have a very small diagram. Here I consider positive point charge placed at a point O. It produces electric field, the space around it. Within the region of electric field, I consider electric field line. Look at this electric field line. In an electric field or in an electric field line, I consider 2 points, namely A and B. So within the electric field only, I consider the point A and point B. The potential at a point A is VA, the potential at a point B is VB. Now I am going to place a unit positive charge at a point B, unit positive charge, or you can also call it as test charge, whose magnitude is 1 coulomb. Now we have to bring this unit positive charge from A to B, one point to another point within the electric field. Within the electric field, we know that there will be an electrostatic force. Electrostatic force. So against this electrostatic force, we need to bring a unit positive charge from point A to point B. Again, work is needed. So we are doing some amount of work done in order to move the unit positive charge from A to B. Work done we are doing. Work done. Now potential difference between these 2 points can be defined as, because these 2 points, point A, point B, the potential is different. The potential at a point B is VB, the potential at a point A is VA. So potential difference between any 2 points in an electric field is the work done in moving a unit positive charge or a test charge from one point to another point against electrostatic force without producing any acceleration in the charge. The same thing what we learned in case of electric potential. There is a similarity between electric potential and potential difference. The same point charge, same point charge. But in case of electric potential, we are bringing unit positive charge from infinity to the particular point in an electric field. That work done gives electric potential at that particular point. But in case of potential difference, we are not bringing the unit positive charge from infinity to the particular point. We are moving within the electric field between any 2 different points, say A and B. So within the electric field, I am bringing or I am moving a unit positive charge from A to B like this. To move this unit positive charge or a test charge, we are supposed to do some amount of work done. Why? Because there will be electrostatic force. So against the electrostatic force we are moving, so work done is needed. That work done in order to move a unit positive charge from point B to point A against electrostatic force gives potential difference between the 2 points. Even in this case also, the acceleration produced in the charge is 0. Potential difference mathematically expressed as like this: delta V is equal to VA, that is a potential at a point A, minus VB, that is potential at a point B. Also you can write it as is equal to work done in order to move a unit positive charge from B to A. So these two are very important fundamental concept in order to understand the remaining concept and derivations: electric potential, potential difference. Both are very important. Both electric potential and potential difference both are scalar quantity. SI unit of electric potential, just I will write EP, electric potential, and potential difference is volt. Electric potential and potential difference are scalar quantity. It has no direction, it has only magnitude, and SI unit of electric potential and potential difference is volt. And one more thing, potential difference at infinity is taken as 0. In the previous explanation only, I told you that at the point of infinity, electric field and electric potential is taken as 0. And there is a lot of difference between potential difference and potential energy difference. Just now I explained. In case of potential energy difference, we did not use unit positive charge, we used a charge Q. But in case of potential difference, we used test charge or unit positive charge. Okay. So SI unit of potential difference on electrical potential is volt. Then when does the potential difference between any 2 points is said to be 1 volt? Question mark. When does the potential difference between these 2 points is said to be 1 volt? Similarly, when does the potential or electrical potential is said to be 1 volt at the point A in an electric field? So first I am going to define this. The electric potential at a point is said to be 1 volt if 1 joule of work has to be done in order to bring a unit positive charge of 1 coulomb from infinity to the point A against electrostatic force without producing any acceleration in the charge, which means what we are doing the work done, that should be equal to 1 joule. Suppose if you are doing 1 joule of work done, then electric potential at a point A will be 1 volt. If you are doing 2 joule of work done, then electrical potential at a point A will be 2 volt. So again I am going to define 1 volt at a point A. Electrical potential at a point is said to be 1 volt, or electrical potential is said to be 1 volt if 1 joule of work has to be done in order to bring unit positive charge of 1 coulomb from infinity to the point A against electrostatic force without producing any acceleration in the charge. Okay, let us define 1 volt in case of potential difference. When does the potential difference between these 2 points is said to be 1 volt? Again the same thing. If the work done, what we are doing to bring a unit positive charge from B to A within the electric field against electric force is 1 joule means, then the potential difference between these 2 points is equal to 1 volt. If the work done is 2 joule, then the potential difference between these 2 points will be equal to 2 volt. So we can define like this: potential difference between any 2 points in an electric field is said to be 1 volt if 1 joule of work has to be done in order to bring unit positive charge of 1 coulomb from one point to another point against electrostatic force without producing any acceleration in the charge. Okay, these two are very important for 1 mark. Next concept is or derivation, electric potential due to an isolated point charge or simply the point charge, both are same. The question will be like this: derive an expression for electric potential due to an isolated point charge for 3 marks. So here our intention is we need to find electric potential at any point in an electric field due to an isolated point charge. So look at the diagram. So I consider an isolated point charge or positive point charge placed at a point O. This point charge produces electric field, the space around it. So in the region of electric field, I am writing one electric field line, So in an electric field lines, the point P I marked at a distance of R from the point O. So we need to calculate the potential at a point P due to isolated point charge. According to the definition, what we learned for electric potential, it is the work done in bringing unit positive charge from infinity to that point gives electric potential, which means we need to bring a unit positive charge from infinity to the point P against electrostatic force. Last discussion, we noticed that the work done in order to bring a positive charge or unit positive charge varies from point to point. So another 2 points I am going to consider in an electric field A and B. So I am going to place unit positive charge at a point B. Then according to the Coulomb's law, electrostatic force acting on the unit positive charge Q naught. So the magnitude of electrostatic force acting on Q naught, which is placed at a point B, is given by F is equal to 1 over 4 pi epsilon naught Q into 1 coulomb of charge is there, that is 1, divided by what is the distance between this point charge and unit positive charge, x, according to Coulomb's law, x square, equation number 1. Electrostatic force which is act on unit positive charge in an electric field. Now to calculate a small amount of work done in order to displace the charge or unit positive charge from B to A through a distance dx, work done is needed because there is a electrostatic force. Small work done in moving unit positive charge or a test charge from where to where we are bringing or moving from point B to A against electrostatic force is given by since we are displacing through the small displacement dx, the work done is also small amount of work done dw, force into displacement, that is dx. So we can write dw is equal to f dx cos theta, where theta is equal to 180 degree. Why 180 degree means The electrostatic force is in this direction, whereas the work done is opposite to that. So here we have 180 degree. Because 180 degrees minus 1, so dW is equal to minus F into dx, equation number 2. So this is a small work done or small amount of work done in moving unit positive charge or test charge from point B to A against electrostatic force minus F into dx. In other way we can write the negative sign indicates the direction of work done is opposite to the direction of electrostatic force, like that also you can write for the negative sign. Now I am calculating total work done in order to bring or in order to move a unit positive charge from infinity to a point P against electrostatic force. So work done in moving unit positive charge from x is equal to infinity to x is equal to r against electrostatic force. W is equal to, it can be calculated by using integration from where to where we are moving from infinity to r. From infinity to r, already we calculated a small amount of work done, that is dW. Then W is equal to integration of infinity to r dW. What is dW? We have minus F dx. Then W is equal to integration of infinity to r. We have a value for F, that is 1 over 4 pi epsilon naught. Q into 1 is Q divided by x squared. So minus sign I will write here, 1 over 4 pi epsilon naught. Q into 1 I am not writing, I am multiplying Q into 1, it becomes Q divided by x squared into dx. So minus Q divided by 4 pi epsilon naught integration of infinity to r. The remaining thing is 1 over x square into dx. Again I am doing some simplification. W is equal to minus Q divided by 4 pi epsilon naught integration of infinity to r. 1 over x square can also be written as x to the power of minus 2 into dx. Now we have to do the integration of x to the power of minus 2 into dx, a basic integral formula we are using. Integration of x to the power of n into dx is equal to x to the power of n plus 1 divided by n plus 1. So this is a basic integral formula. So in the place of n we have minus 2. Integration of x to the power of minus 2 dx is equal to, in the place of n what we have, minus 2 plus 1 divided by minus 2 plus 1. So integration of x to the power of minus 2 dx is equal to minus 2 plus 1 is minus 1 divided by minus 1. So integration of x to the power of minus 2 into dx will be equal to minus 1 over x. This part is not necessary to write, but you must know. Directly you can write integration of x to the power of minus 2 dx will be equal to minus 1 over x, directly you can write. So I am going to substitute. W is equal to minus q divided by 4 pi epsilon naught. After the integration, what did we got? Minus 1 over x. Upper limit is r and lower limit is infinity. Then W is equal to minus, here I can cancel minus and minus, get cancelled. Then Q divided by 4 pi epsilon naught So x is a variable. To the variable I am substituting upper limit, minus to the variable I am substituting lower limit. So 1 over r minus 1 over infinity. Since 1 over infinity is 0, 1 over infinity is 0, we can leave this. The remaining thing, w is equal to q divided by 4 pi epsilon naught 1 over r. So this equation can be simplified like this: 1 over 4 pi epsilon naught q divided by r. This is the total amount of work done in order to bring a unit positive charge from infinity to a point P against electrostatic force. Since we are talking or we are bringing unit positive charge, which means the charge of 1 coulomb, for charge of 1 coulomb, W is equal to V. So this work done is stored as electric potential. V is equal to 1 over 4 pi epsilon naught Q divided by R. Which means V is inversely proportional to R. As the distance increases, electrical potential at a point P goes on decreasing. So this derivation is important for 3 marks. Derive an expression for electric potential due to an isolated point charge or due to a point charge. Here, look at the graphical representation of variation of electric field and electric potential with the distance. Along x-axis, it represents distance. Along y-axis, it may represent electric field and electric potential. Here, the blue color line indicates electric field, whereas the yellow color line indicates electric potential. Look at the variation of electric field with the distance, the variation of electrical potential with the distance. Because the electric field varies square of the distance, whereas the electric potential varies distance, there is no square. So this is the graphical representation of variation of electric field and electric potential with distance. The next concept is electric potential due to a system of charges or principle of superposition of electric potential. Just now we discussed electric potential due to an isolated point charge, means single charge. Now we are going to understand electric potential due to system of charge. Now I consider group of charge, this is nothing but system of charge. Group of charges Q1, Q2, Q3, Qn placed at a distance of R1p, R2p, R3p or Np respectively from point P. You just look over this diagram. Group of charges I consider up to n number of charge Q1, Q2, Q3 and up to Qn. The distance between the point P and the Q1 is R1p. The distance between the point P and Q2 is R2p. The distance between the point P and the Q3 is R3p. The distance between the point P and the charge Qn is Rnp. So there is a potential at a point P due to Q1. There is a potential at point P due to Q2. Potential due to Q3, potential due to Qn. Separately I am right. Electric potential at P due to charge Q1 become V1 is equal to 1 over 4 pi epsilon naught Q1 divided by what is the distance? R1p, equation number 1. Then electric potential at point P due to charge Q2 is V2 is equal to 1 over 4 pi epsilon naught Q2 divided by R2P. Equation number 2. Similarly, electric potential at point P due to charge Qn is Vn 1 over 4 pi epsilon naught Qn divided by Rnp. Equation number 3. Electrical potential at point P due to charge Q1 is V1. Electric potential at a point P due to Q2 is V2. Similarly, electric potential at a point P due to charge Qn is Vn. Since electric potential is scalar quantity, the total potential or resultant potential at a point P is equal to algebraic sum of individual potential, which means the total potential is equal to V1 plus V2 plus V3 Vn. So V is equal to, what is V1? We have 1 over 4 pi epsilon naught Q1 divided by R1P plus V2 1 over 4 pi epsilon naught Q2 divided by R2P plus, directly I will write Vn, that is 1 over 4 pi epsilon naught Qn divided by Rnp. So in this 1 over 4 pi epsilon naught, 1 over 4 pi epsilon naught, 1 over 4 pi epsilon naught, I can take it as a common. I will write here total potential V is equal to 1 over 4 pi epsilon naught. I have taken common. Then I am using summation of I is equal to 1 to n, then Qi divided by Ri into P. Just check it out whether it is holds good or not. 1 over 4 pi epsilon naught is a common. So summation of I is equal to 1 to n means in the place of I we can give 1, 2, 3, 4 up to n. Let us give 1, Q1 divided by R1P. Q1 divided by R1P. If we given 2, Q2 divided by R2P. Q2 divided by R2P. Likewise, if we given n, Qn divided by Rnp. So that is holds good. It's the final equation. Electric potential due to system of charge, that is principle of superposition of electric potential. So in this class we learnt electric potential, potential difference, potential energy difference, and one derivation we learnt, electric potential due to a point charge or due to an isolated point charge. So we learned the variation of electric field on electric potential with a distance. And the last we learned electric potential due to system of charges or group of charges. In the next class we will discuss another few concepts. Until then, take care, have a nice day, thank you.